Good evening, everyone. I am Babulkar, Technical Events Coordinator for Civil Engineering Sectional Committee. And today is the 10th lecture of our lecture series on hybrid multi-story design, the structural design of hybrid multi-story buildings using Eurocodes. And today we are having the second lecture on Flexural Shear and Torsional Shear. And I would like to appreciate Professor Jayasinghe's commitment in conducting this lecture series. Actually, even from university students, we are receiving many positive feedbacks about this lecture series. So thank you very much, sir. And over to you, sir.
Okay, Bandukar, thank you very much. Just give me 1 minute until I get the notes loaded.
Okay, sir.
You all can see it? Yes.
Yes, we can see.
Right, so last time we talked about torsion. And we talked only the very basic stuff, like, how to find whether a section can take torsion and so on. But today we are going to find the reinforcement requirement. So I told you that, torsion consists of two parts. One is equilibrium torsion, the other one is compatibility torsion. So this equilibrium torsion, you must provide reinforcement to resist it. When you have compatibility torsion, you can ignore torsion by going for a torsionless system. So in the case of brick design, we use this torsionless system a lot. But in case of buildings, especially places like transfer plates, transfer beams, you have to be concerned about equilibrium torsion. And I showed with examples with rigid arms how to find the torsional moment on a beam when you are creating a model. So then we also looked at torsional shear. So torsional shear will cause diagonal cracks right round. So they can make the beam to fail. So if there's a beam subjected to torsion, we must provide the reinforcement. The reinforcement will consist of additional longitudinal bars and links. And I showed the shape of the link as well. Right. Now we will look at this particular situation, and we'll also look at this particular equation. Qi is torsional shear stress multiplied by thickness, Q. And Q is the torsional shear that is flowing around it. So we have an equation where AK is the area surrounded by the center line, AK. So first we look at how to prove this equation. So this equation is used a lot when you are finding the reinforcement. So you can just have a quick look, and that is Q is equal to capital T divided by 2AK. And I'm going to refer a diagram like this. So let's look at it. And this is how the torsional shear flows. And you can see torsional moment is tau, TED, and the area surrounded by this particular center line is AK. And Q is equal to TED over 2AK. That is the equation we are going to prove. And these are extract from the code. So code gives this diagram, and if I try to use the diagram that is available on the note before I move on to the white sheet, here you are. This is how the torsional shear flows. Because can you remember last time? Banduk, I hope you can remember. We said when you are designing a rectangular section, we design it as a hollow section and
Yes,
then
sir.
provide the reinforcement requirement, right?
Yes,
And
yes, sir.
also, if you look at the shape of the link, can you remember this shape I have drawn and shown you?
Yes, sir. We did that.
This is the torsional link, right? So any section subject to torsion, we need torsional link. Then you have to look at this particular diagram, and you can see how the torsional shear occurs, right? So it goes right round, and in torsional shear also tension will be taken by steel, compression will be taken by concrete. So to determine the longitudinal forces, we have to consider the whole perimeter, whereas to determine the vertical links, we consider one side. So I'll come to that little later. And this is the equation we are trying to prove. T is equal to AKQ. And if you look at this diagram, just have a good look at this diagram, because I'm going to draw it again. And I'm going to find the, this, I'm going to show you how to prove this equation, right? So the equation is this one. T is equal to AK times Q. Or Q is equal to T over 2AK. So just have a good look at this particular diagram. Now I'm going to stop share, and I'm going to move to the white sheet. So basically what we have is this diagram. This is the diagram, and this is the center line. Torsional shear stress is tau I, and this is uniform thickness, so Ti. Tau I Ti is equal to Q in kilonewtons per meter. In kilonewtons per meter or newtons per millimeter. Then torsional moment T is equal to torsional force multiplied by lever arm, sigma. And torsional force on this face is equal to Q times Q. And if this is A1, this is B1, center lines, A1, B1, Q times B1, but Q1 times B1 is a force, and it has to be multiplied by A1, because moment is equal to force multiplied by lever arm, plus Q times, if you take this face, A1 multiplied by B1. So that is 2Q A1 B1. A1 B1 is AK. So T is equal to Q AK. Is that clear, Bandhuko?
Yes, sir. That is clear.
So that's a simple equation that is applicable. Right. Now we look at the code provisions. So I'll start sharing, and here you can see the Euro code. We have to go to section 6 because we are designing. Go to 6. So this is the code. This is all about punchy shear. Okay. Now here you get torsional shear. So if you look at torsion in the code, it's a very small section. And this is the equation that we have just proved. Then it gives this diagram, which tells about the shear force on a wall. Then it gives this particular equation. It gives this particular equation, which says the longitudinal reinforcement, the total longitudinal reinforcement requirement is a function of the torsional moment applied, 2AK and UK. UK is the perimeter of the member. UK is the perimeter of the member. And that's all. So it tells us about how to find the longitudinal reinforcement, but it doesn't give an equation for how to find the shear link requirement. But I'm going to show you how to find that. So it gives this equation, which says sigma ASL FYD over UK is equal to TED over 2AK cot theta. So that is the only equation given, 628. Then it gives another equation, 629. Can you remember last time we used this equation to see whether the torsion is excessive or not? Because there's no point in finding torsional reinforcement if torsion is excessive, right? So we use that equation, and TRD max is given by this equation. Again, we sorted it out, and VRD max, I showed you that there's an equation given under direct shear. VD is the actual shear, TED is the actual torsion. So we got an answer of 0.92. Then we said, okay, that particular section is okay because the torsional moment is only 24 kilonewton meters. That's all. And it ends here, and this equation is valid just to see whether torsional reinforcement is needed. I mean, if this equation is satisfied, you don't need any reinforcement. But generally, we don't have any section without shear links. So but what this basically says is, if the torsion is very small, no need to provide torsional shear reinforcement. So then basically, most of the structures, when you analyze three-dimensionally, the torsional moment is close to zero. So if the torsional moment is close to 0, you don't need special treatment for torsion. So that's the meaning of this particular equation. And our usual practice is we don't worry about torsion. We simply worry only about shear, direct shear, not torsional shear. But if the torsional moment is there as for the equilibrium torsion, then we have to worry about this equation. So this equation we never use, but we use the fundamental behind this one. Fundamental is, if the torsion is small, don't worry. That's what this says. Because if this value is very small, then you don't have to worry. On the other hand, what it says in other words is, if torsion is close to 0, only direct shear is available. Make sure the section can resist direct shear. But on the other hand, if there's torsion, if there's direct shear, then it must fulfill this condition. So the equation that is used is 629. We generally don't do 631. 631 is a fundamental condition that is given. And so the two equations that we use are 629 and 630. And we'll be using 628 as well. So there are three equations that we can use. This equation is to find the longitudinal reinforcement. These two equations to find whether the section is adequate. And if it is a rectangular section is not adequate, don't increase the depth because you are not going to gain much. Always increase the width, because we know square sections are far better than rectangular sections when it comes to shear. Is that clear, Bandhugal?
Yes, sir. That is clear.
Very good, right? Okay. So now we have this equation, right? And that is equation 628. So what I'm going to do is we'll just look at the proof that is given in Mosley and Banji book. So I will share the note. Share the screen. Torsion. So we have to prove two equations. One is this one, where we have the diagonal torsion, the longitudinal reinforcement. The other one is vertical reinforcement. So we now look at the fall perimeter. What is the perimeter? Perimeter is UK. And if you look at UK, we just look at the equation, the example. The wall width is 100. T effective is 100 millimeters. This is the example we did last time. The area underneath is this. And what is UK? UK is the perimeter of central line. UK is the perimeter of the central line. So that is 2B1 plus 2A1, or otherwise B plus H minus 2T effective multiplied by 2. B plus H is the actual dimensions, B plus H, minus 100 this way, minus 100 this way, sorry, B plus H. The equation is written as B plus B minus T effective plus, it is not plus, actually it is B plus H. B minus TF multiplied by, oh sorry, plus yes, because we are looking at the perimeter. B minus TF plus H minus T effective multiplied by 2 is true. That's correct. So that is, this plus this plus this plus this. So 1400. So that is the center line. Then what we do is we look at this diagram, and the torsional shear will give a shear stress of force of Q times UK, and there's a force triangle as you can see here, and this is Q times UK. This is Q times UK divided by sine theta, and then cos theta will give you Q times UK or tan theta as the horizontal force. So who will resist this horizontal force? So we have this equation, Q times UK divided by tan theta as the horizontal force, and Q means T over 2AK times UK over tan theta, and that force is resisted by the reinforcement, the horizontal reinforcement, that is ASL Fy Lk divided by 1.15, right? And so you'll see it gives ASL Fyd or UK equals TED over 2AK cot theta. Right. So I'm just going to show you the code equation, and the code equation is given as, I'll just stop share. This is the code equation. I copied the equation given in code, equation 628, and the horizontal component is Q UK over tan theta, and Q is T over 2AK. You can substitute there, UK over tan theta, and that is the force that has to be resisted by horizontal reinforcement. So this part is FYD. This is FYD. So ASL FYD, and here UK can be brought here, is equal to TED or 2AK. This AK, and 1 over tan theta means cot theta. So this is the equation given in the code, and this is the equation that we are going to use, right? So the equation that we are going to use is T over ASL FYLK or 1.15 equals TED 2AK UK over tan. This equation, right? And what you are looking for is ASL, longitudinal reinforcement, additional longitudinal reinforcement. Okay, so what you get is, if I start sharing the node, and if I look at this is ASL is equal to TED UK cot theta divided by 2AK 0.87 FY LK. So the equation is ASL is equal to TED UK cot theta divided by 2AK times 0.87 times FYL, and if I stop share, you can look at the white sheet. Now this is the equation that I have written from earlier one, and ASL is equal to TED UK 1 over tan theta is cot theta, 2 AK, FILK divided by 1.15 means 0.87 FIL. So this is the equation that we need to find the longitudinal reinforcement. This is the exact equation that is given in the code. So that equation is no problem. So the only thing is this is a different version of the same 628. Equation 628 is this one, but a different version because equation 628 given in the code is FYD over UK equals TED 2AK cot theta. So here UAK comes here, FYD goes there as 0.87 FYL. Is that clear, Bandhuka?
Yes, that is clear, sir.
Yeah. So basically there is no problem, the same equation, right? Equation is the same and it is given in the code. Now let's see how we deal with the next one. That is the vertical links. So for the vertical links, so we'll you can just look at this particular equation because I'm going to show you how we get there. So if you look at this diagram now, here you can see this h cot theta. Over h cot theta, what is the force? Vertical force. Over this distance, the vertical force is QH. And if you are providing some reinforcement, the reinforcement should resist this QH. The reinforcement should resist this QH. Right? So if you are providing one reinforcement, it should resist this QH, but we may have number of reinforcement at S spacing S. So because of that, we can actually get rid of this H in the equation. We can replace H with HS. So you can look at this one. So it says the vertical force is equal to force in steel divided by 1.15 is equal to Q times H. But if you are going to have links at a closer spacing than H cot theta, then the force will be SOH cot theta. So this H and H will cancel out. Then you will find ASWFY K or 1.15 is equal to Q times S over cot theta, but Q is equal to TED over 2AK. So from that you can get this equation. So the equation is ASW FYK over 1.15 is equal to Q times S over cot theta, and the final equation we are looking for is ASW over S is equal to TED over 2AK 0.87 FYK cot theta. So I will stop share now. So we have this equation, and we have to see how to get this from this. So we get ASW or FYK and into 0.87 is equal to Q is TED over 2 AK S times cot theta. So this S can be brought here and this can go this way. So you get this equation. So that equation is not given in the code, but it's given in textbooks. So we will be using this equation. So that's why I said the solution for torsional design is Excel spreadsheet. Because all the equations are not given in the code. So we are using some equations from textbooks. It's a long procedure. So the ideal thing is, because when the procedures are long, we can easily make mistakes. So the ideal way to prevent any mistakes in torsional calculations that you often don't do, that is also another problem. If you are doing, even if it's a complicated calculation, we are doing it very often, then it's not a problem. But this is not a calculation that we don't, that we would need. We need it only once in a while. So what is the best solution? Best solution is, first understand go through the example given and write a small computer program on a spreadsheet with all the conditions in, so that you can calculate the torsional shear link requirement easily with additional longitudinal reinforcement. Is that clear, Bandhuga?
Yes, sir. That is clear.
Right. Okay. So what we are going to do now is, we'll go back to the design example. So this design example, the theory is covered in a number of steps. Right. So that is the theory part. So shall we have a quick look at the design example right from the beginning? Because now we know all the equations, Bandhuga.
Yes, sir. That's better, sir.
Good. That's better. Is that right?
Yes.
Like, because some may not remember the whole thing.
Yes.
So the design example is a beam of 300 and 600 depth, 300 width, 540 effective depth. Now in this particular beam was originally designed to carry a vertical load of 108 kilonewtons per meter. So that design was done without worrying about torsion. Then they found, okay, this particular beam can be subjected to torsion as well. If that is the case, what are we going to do? Okay, we have to provide torsional resistance. Now to see whether this torsion can be taken, the first step is convert this rectangular section to a form that we can use in calculations. So for that, the guideline is given in the code, which says the effective thickness is A divided area of the section divided by the perimeter. Right? Effective thickness is area divided by perimeter. Area is 600 by 300. Perimeter is 900. 900 here, 1800. So you can see it is 900 into 2, 1800, 600 by 300, 100 millimeter. So that is the effective thickness. That is clear. Is that right?
Yes, that is clear.
Yeah, right. Then we need another parameter, that is the centerline AK area. That area is 200 multiplied by 500. 200 multiplied by 500. See here, 200 multiplied by 500. Then we need this perimeter. That perimeter is 200 plus 200 plus 500 plus 500, 1400. So that is also 1400. So those are the important parameters that we need to solve a problem. So now we have all the parameters that we need to solve this particular problem. Now, when you are designing, for convenience, it was considered as simply supported. Right? So the first part of the design will be finding the bending, the reinforcement, and then finding the shear requirement, and then they found that the strut angle is 20 degrees. So the shear failure is going to be at 22 degrees. So this is a shear design. So the maximum shear is on the section is 308 kilonewtons, and the maximum shear resistance is 530 at an angle of 22. Because we did examples, so I'm sure you can recall it. And this is the first part of the design where the beam has been designed for flexure and beam has been designed for shear. And we know the amount of shear link required, and the shear link requirement is given as ASWS is 0.475. Just keep it in mind because that's an important information that we can use later. Now we are going to do the torsional design. Now what is the first thing in torsional design? Make sure the torsion is not substantial so that this small section can resist it. Although this 600 by 3 is a significantly large beam, for torsion it's not a large beam. Why? For torsion, it's a rectangular beam, so it's not a large beam. On one side, it has only 300. For something to be torsionally large, it has to be something like 400 by 600, or 500 by 600, or 600 by 600. Those are large. But this particular section is not a large section as far as torsion is concerned. For torsion, it's not a large section. But for bending, it is a large section. So, for example, even as singly reinforced, 600 by 300 beam can carry about 500 kilonewton meters. So, it's a substantial moment. But when it comes to torsion, it can barely carry 24. Because you can see when this condition was checked, we came pretty close to 1, the limiting value. So what you have to keep in mind is this section is very weak because it's a rectangular section. But when we do this check, if it fails, don't increase the depth. That is not going to help you. You must increase the width of the section. Move from rectangular to square, then you will be through. Is that clear, Vandukar?
Yes, sir. Yes, that's clear, sir.
That's clear, right? So we have to check it. At DRD max, this equation is given, and nu also 0.528. That's the equation given in the code. So last time we calculated TRD max and we got the value close to 73. And so this is 24 divided by 73. This value was also calculated. That is 308 is the value and maximum is 530. Can you remember I showed you those values earlier? VD is 308, VRD max is 530. This is a calculated value. And if you look at this one, you can clearly see this maximum shear on the face of the face of the column is 308, and shear capacity is 530. To calculate VRD max, there's equation given in the code, and we have calculated that value for an angle of 22. Now, why this angle of 22 is important? That means shear failure is going to happen at 22 degrees. Then torsional failure will also happen at 22 degrees. So when you are substituting for theta, you can now substitute 22. Because everywhere you get theta. Right. Now, this is the theory part that we just discussed. And first we will calculate the additional links. ASWS is equal to TED over 2AK 0.87 cot theta. Cot theta is cot 22. Cot 22 means 1 over tan 22, and 1 over tan 22 is 2.5. You can just check it. Can you just check 1 over tan 22? What is the value, Bandhuga? 1 over tan 22?
2.475.
Yeah. So we consider 2.47 as 2.5, right? So cot 22 is equal to 1 over tan 22 and 1 over tan 22 is 2.47. So we substitute it as 2.5. Fyk is 500. This 0.87 is a partial factor of safety. And we earlier found this area is 2 into AK is 100 into 10 to the power 3. And just substitute. And torsional moment is 24 multiplied by 10 to the power 6. And you get ASWS as 0.110. Now you have to be careful. So I'm going to stop share to explain that. So now we have a section. And we are trying to see what's going on. So we have these links. So when shear, direct shear happens, so this will all go into tension. So we have two legs. But torsional shear occurs differently. It is going right round. So we cannot have two legs at once. Each leg should be considered separately. So that's why we consider only this leg. So this is ASWS is single leg. Here ASWS represents both legs. Is that clear, Bandhuka?
Yes, sir. That is clear.
So this is 1, this is 2. Then you get the total link requirement will be S plus twice ASW2 divided by S. This is the total link requirement. Is that clear?
Yes, yes.
Right. Okay. So I'll go back to the screen. So what is the total shear link requirement? Will be 0.475 comes from the earlier one. Can you remember I showed you the shear link requirement that has been calculated as 0.475. See, the shear link requirement is SWOS is 0.475. And in shear, there's an additional longitudinal force that is 385. So this 4.475 plus 2 times 0.110, 0.695. So what are we going to do? We have to find ASW. So let's say if we are providing 8 mm stirrups at 125 centers, so ASW is 50. 50 divided by 125, 0.805. Is that right, Bandhu? ASW is 50. 50 divided by 100. Yeah.
50 divided by 125 is 0.4.
0.4.
Yes.
All right. So these for two legs, right? So 0.4 multiplied by 2, 0.805. Okay.
Yes.
Because this has two legs. ASWS is now representing the shear link. Because it has two legs. So you have to multiply. This is not 50 divided by S. This 100 divided by S. Area of 8 mm reinforcement is 50. But ASWS is actually representing two legs. So that is 100 divided by 120. Can you see that?
Yes.
In shear links, what is ASWS? ASWS is area of both links, both legs. right? So we have to carefully do this. So that is, if it is 8 millimeter, each leg is 50 millimeters squared. 2 legs means 100 divided by 125. 100 divided by 125 is 0.8. So the spacing has to be 125. And then there's another rule. There's another rule. What is that rule? That rule says, if you are providing links, the maximum spacing of link should be less than UK divided by 8. What is UK? 1400 divided by 8. And UK is, can you remember UK? UK means 1400. And UK means addition of this length perimeter, center line perimeter. On the center line, right? So you get 1400 divided by 8. This also should be checked. 1000. So that is 1400 divided by 8. What is the value, Bandhuka?
175.
Yeah, 175. So the link spacing should be less than 170. There's an upper limit. The upper limit is equal to that center line length divided by 8. So you have to keep in mind there's a maximum spacing for torsional links. Recommended maximum. Recommended maximum is UK divided by 8. Is that clear?
Yes, sir.
So now we have got the link spacing. Link spacing is T8, and then you can check it at different other sections as well. Right. Then because this torsion is not going to so generally when you design for torsion, you have to look at the torsional moment diagram on the structure that you have analyzed. If it's a transfer beam, you will find different sections have different torsional moments, so you have to repeat this design at number of sections and then decide what is the common thing you are going to adopt. Is that clear?
Yes.
Because you know it's not uniform, because most of the time torsional moments vary like bending moments. So you have to find the critical sections and check and come to a conclusion. In this example it is not there because we are just checking whether it can carry 24 kilonewton meters torsional moment at the center. That's all we are doing. But in the actual situation, from section to section, you will get different torsional moments. So that has to be checked, and the maximum should be found, and then check the condition less than 1 with the maximum torsional moment with maximum bending. Okay. Now we have to find the longitudinal reinforcement, and I have shown you the equation, and it's based on UK value. So 966. This additional longitudinal steel should be provided by 6 H16 bars, 1200. One in each corner and one on each side faces as shown in 630 CE. The additional longitudinal tensile force is 385 resulting from the design for shear will be carried for by appropriate curtailment of reinforcement, the main tensile resistance. So we just look at this diagram. These are checked to see whether 24 kilonewton meters of torsional moment can be carried. And if you look at the figure, here you can see every corner 16 millimeter bars, 2 additional bars here, 2 additional bars here. So because it's subject to torsion, you have to provide additional bars right round. Why? Because this crack is going to propagate along the beam. So every possible place we must provide longitudinal reinforcement and make sure the separation or the crack will not be visible to the eyes. Just when you just look at it, crack is there but not visible. To make sure the crack is there but not visible, what we do is we provide all this extra reinforcement on the perimeter. Is that clear, Vandhuka?
Yes, sir. Yes, sir.
So that is another important thing that you have to consider, right? And right. So that is something that is very important. Only in the case of transfer beams. Other places we simply ignore. We don't worry about it. But if it occurs, then you must be careful. Why? If it starts failing, there's nothing to stop it. Now these days we all think, okay, something is failing, just wrap some fiber FRP, fiber reinforced polymers, like carbon fiber, and we can give a little push to the structure by increasing the moment carrying capacity of beams. But if the torsion failure occurs, it's a critical failure. It will continue to happen. So because of that reason, it's very, very important that we provide torsional links and resist torsion. Okay, wonderful.
Yes, yes.
Now, any questions on the chat?
So far, there's no questions.
Okay. Now then there's another important thing that you have to consider, right? That is, I'll first explain it, then we'll look at the code. Now this is also related to shear. Now let's say we have a slab connected to the beam. What do we do? Oh, there's a slab. In the span section, we say behaves as a flange beam. Is that right? So if it is a flange beam, there will be some stresses here. And that means there can be some shear failure. And how to prevent this shear? We can prevent it by using double action. So what we do is, we'll make sure this reinforcement goes like this. The other reinforcement comes like this. In addition to all this, we will provide some additional reinforcement. Then if that is the case, can you get some cracks here? You say, okay, I mean the chances of cracking is very minimal. Why? Because there's plenty of reinforcement continuing across the section, and section will not have problem. How do we check it? How to check it is not straightforward. Why? Because we have a bending moment diagram. And what it says is, get the bending moment diagram. So this is L by 4. This is L by 4. Now in this one, where do you get the maximum change in moment? Maximum change in moment, this pattern will occur in this portion. And Then we find how much force is actually carried in this one between these 2 points, and that difference in force is the one that caused this shear failure. Then what are you going to say? Check and see whether the shear failure can occur. The shear failure can occur along a beam. Make sure you provide enough reinforcement. So that is something that is available on the code. We have to make some provision, and fortunately what happens is we provide top reinforcement, we provide bottom reinforcement, we continue this reinforcement to the across the joint, across the beam. So what happens? Most of the time, even if you don't do this calculation, still the section will be okay. But if the flow is heavily loaded, then they recommend doing this calculation and checking whether the beam has a problem. So I'll show you where you can find this information on Eurocode. Now torsion is over, punching, then you get punching. It comes before torsion. There you go. What it says is there can be problems along this beam slab junction, but in a typical reinforced concrete slab, this will not be a major problem at all. But then in that case, where could this be the problem? Now you look at this diagram, just turn it by 180 degrees. What do you get? Inverted T foundation. The inverted T foundations are heavily loaded. These slabs are very lightly loaded. So in the case of inverted T type foundations, you might have to check for this particular condition. But to check, you need a bending moment diagram, and then check it, and the transverse reinforcement requirement is given by this particular equation. And we'll again look at an example just to learn what has been done, right? Because the code covers up to this point with different values. The important thing that you have to keep in mind is for this particular shear, the critical shear starts from 26.5 degrees up to 45. So here you can see cot theta varies from 1 to 2.5, 2.0. Can you remember earlier it was 2.47? Now it is 2, right? Is that right, Madhuga?
Yeah, earlier
Can
it
you
was
remember?
2.
The
Yes.
angle was 22 to 45.
Yes.
But for this particular shear, it is 26.5 to 40. So you get shear along this particular surface. Can you see? Diagram is very clear. It's a diagram given in the code. And what happens? Can you see this force FD? What is the force here? FD plus delta FD. So what happens? This side is having more force than this side. So you can't have equilibrium. It might break. So we have to make sure there's additional precaution to assure that this flange will remain intact with the web. Otherwise, if it cuts, flange will separate, the moment carrying capacity of the beam will drop drastically. Is that clear?
Yes, yes, sir.
Right. Okay. So we'll have a quick look at the example. Somewhere in this note, one example was given. So these are all that we use to study about concrete, cover to concrete, flexure, then shear. We all learned a lot about this. So this design for shear, the design example. So if somebody goes through this note, you can learn a lot because there are design examples as well. There's one small mistake in one of these equations, but I showed the place. Today we'll skip it. And then how to find the minimum reinforcement of links and so on. Now here you get this particular example. And the transverse shear reinforcement is given by this equation. And the period crushing of the compression starts in the flange. It says VED should be less than a particular value. That we can check. And the minimum angle will be 26.5. So then it talks about the equation 6.21. And that is this equation. So this example is given. And we are supposed to find the shear at this particular face over quarter of the distance of the beam. It's quarter the distance of quarter the span of the beam. So we just look at it. That is just to find the reinforcement. Now you can see some complicated calculation. What is the meaning of that? So I'll stop share, then I can explain it. So we have a beam, flange beam. So on this side, if at force FD, so FD1, and we are going to get the failure at this particular interface. So what the code says is, bending moment diagram goes like this. These two quarter points will experience a lesser change in moment. So if the beam is going to fail, it will fail here, or it will fail here. It will not fail. So it goes well with the shear requirement as well. So this is L by 4. And what it says is find this bending moment. So that complicated calculation we have seen is just to find the bending moment variation. So I'll share again. So the change in moment is 149. Then you can find the force is D minus HF by 2, the lever arm. And then that particular example has flanges on both sides. So you have to find what is the exact force. And the exact force has been found as 96 kilonewtons. If you just look at it carefully, this is self-explanatory. Everything is given. Then you calculate the stress, 0.43. And it says, if the stress is low enough, you don't have to do anything. But at the same time, it's checked for crushing of the compression strut, 26.5 degree angle. So VD max is 5.4 greater than 0.43. So we don't have a problem. Then again, there's a minimum value given in the table. It says if the stress 0.43 is less than a certain value, you don't have to worry. So what actually happens is, in most of the cases, because we are in situ casting, we are providing slab bottom reinforcement across this interface. We are providing slab top reinforcement across the beam. So we have this common interface between the flange and the web. So that is a common area. And if it is going to fail, the stress should be large enough. So here what has happened is stress is so small that is not going to fail even if you don't provide any reinforcement. So that's what you generally find. But in case of inverted T beams that we use for foundations, this failure can happen. So it's not a situation for general straps. Straps we are supposed to check, but generally when you check for a strap will be okay. If that is the case, again, what is the solution? Better write a spreadsheet so that automatically this will be checked, because this is just a useless calculation for most of the slabs. But you have to get these moments fed. But when you have a bending moment diagram, you can easily feed the moment. You don't have to do this complicated calculation as given here to find the variation in moment. So you don't have to do any of these things because these are manual calculations. From the sub 2000 bending moment diagram, you can straight away find what is the change in bending moment, and from that you can work out what is the change in force. And when you know the change in force, you have to make sure that the corresponding stress is low enough. If the corresponding stress is not low enough, you need to provide additional reinforcement. Is that clear, Bandhuka?
Yes, that is clear.
That's clear. So this is not a calculation that you often need to perform. But we have, as engineers, we should be aware that these failures can occur. So when you are doing the detailing, we can be a little generous. That's the whole idea. Like rather than just stopping the reinforcement in the middle, we might take it to the very end of the beam, so that each reinforcement has better anchorage. So each reinforcement will be geared to resist any stress that occur on the surface between the web and the flange. That's all. Okay. But in the case of inverted T-type foundation, because the foundations are designed for very high loads, you will find this particular violation is a significant one. So I will show you this in a later day, because when we might be talking about foundations one day. So on foundation note, I have an example using this particular information. Okay, Bandhuka. With that,
Yes,
shall
sir.
we wind up for today? Because I think
Okay.
now time has come for us to actually move on to columns and the whole building concept.
Okay, sir.
Right? So because I just wanted to create the background, good background, so that when I talk, most of those who have participated will understand it 100%. right?
Yes. Okay, sir.
So now we have created the background. Now now I think time is right for us to move to the real material for the lecture, the course, like lightweight hybrid multi-story construction.
Okay, sir.
Because now we are familiar with Eurocode,
Yes.
then I can show how the Eurocode can be used for optimization.
Okay.
Right? And how
There's
about the chat?
Yeah, one question is there. Sir, could you please explain about shear enhancement near supports in short spans?
Right. Yeah, that's a good question. That's a good question. Right. So what happens is, when you have a beam, now this is for something that is found experimentally. Let's say we have cobblestone. We apply a load here. What is the failure plane? Very high angle. So the code says two things. When you are designing for shear, this is a beam. It says, because here to create a failure, the angle is very high. So it has significant enhancement. So because of that reason, it says don't check shear here. Check the shear D away from the face of the support. Check the shear D away from the face of the support. Whatever the links that you get here, provide the same links up to the support. Is that clear, Bandhuka? Because of
Yes,
this
sir, yes.
enhancement, we are checking D away. Okay? Only because of this enhancement, because at the very close to the support, you can't get shear failures. Got it?
Yes, got it.
So what we do is, we check at D away. And when you are checking D away, this center line, this is the face of the support, this is D away. So this bending moment diagram is, you find there's a substantial difference between these two shear forces. So why we check D away is because of this enhancement. Then it says, if you are going to consider the enhancement, then you have to consider it as some support here, and this is AV. 2D over AV is the enhancement possible. So the way Eurocode handles it is, find the stress here divided by 2D over AV, and make sure that you design for that particular shear stress. Now where are we going to use it? Now let's say we have a pile. We have pile cap. We have these piles. So we have to check this section. And this is very tall. So it's here in between. So we say, when you are checking, use the enhancement, but the enhancement or whatever reduction is 4 times, is limited to 4. Otherwise, if this section is very close to this one, 2D over AV. If AV is very small, you can get 12 times increase or 15 times increase or 20 times increase. But the code says the increase is limited to 4 times the shear stress. So what is the shear stress of concrete? Something like 0.4 for thick sections. So this can be enhanced by 4 times, so it will go up to about 1.6. So instead of using the shear capacity as 0.6, 0.4, you will be able to say the shear capacity is about 1.6. So that's how we make sure pile caps do not fail in partial shear. Why pile caps are so thick? We have a rule for the pile cap. What is the rule? The thickness of the pile cap should be, if this is D, this is D half D by 2. It should be very thick, should be D by 2. So my rule is D by 2 plus 600. So when the pile cap is so thick, can it fail in partial shear? No. So we have rules of thumb like that. We don't use thin pile caps. Always we'll make sure pile cap is the distance between two piles divided by 2 plus 300 millimeters or 600 millimeters. Have I answered the question, Bandhuga?
Yes, sir. It is clear now.
Because whenever you get shear, so if you look at a pile example on pile cap, you will see that this particular 2DO AV rule is has been used. But you can't find any other place where any example that 2DO AV has been used. Any textbook, the only place you can find 2DO AV rule being used is either cobblestone design or the pile cap design. In pile cap design, you have to use 2DO AV rule. Is that clear?
Yes, that's clear.
Right. So no place in any example you can't find it. So basically, we are not using 2DO AV rule under normal situations. But we use 2DO AV rule when you are designing pile caps. But we are actually using this rule. That's why we check D away. Were you aware that why we check D away when you are checking the shear? Earlier, Bandhuga?
Yes, sir.
Yeah,
earlier.
so that is 2DO AV rule, right?
Yeah.
2DO AV rule, because there's an enhancement very close to the support, we check shear D away from the face of the support.
So this 2D OAV rule, we also using embankment pile cap designs.
Oh, yes. That's right. So in highway engineers use it often. Yes. But building engineers hardly use it. They use it without knowing. So that means they check at the face, they don't check shear at the face of the support. They check shear D away from the face of the support because of this 2D rule. 2D OAB rule. Okay, Bandhuka?
Yes, okay, sir.
Right.
And
so any other question?
That's all questions for today, I think.
So today, what is the time? 8:25. I think we can stop, and next time we'll go move deeper into the concepts on cost effectiveness.
Yeah, and also, sir, we are having discussions in issuing a participation certificate for this lecture series, as discussed with you.
Yes. So what we discussed was for participants to offer a certificate to use it in 5 slots. So every 5 slots, a course will be in 5 slots. So a course component will be in 5 slots. So if anybody attending all 5 slots or 5 to 6 slots, we need little flexibility. They get a certificate for that part. Is that right, Bandhu?
Yeah, that's what we discussed.
Yeah. So that way, you'll be able to collect a number of certificates, but you don't have to attend the whole course. So if every time you attend 5 or 6 continuously, no absenteeism in between, then our course modules will be 5, 6, 7 range. So generally, course module will be 5, 6, 7 range. So when you attend all those, then we say, okay, now you are qualified for 1 certificate. So that's the way that we thought of adopting. So Bandhuka will coordinate that.
Yes,
So
sir.
you can work out the necessary details, Bandhuka.
Yes, sir. I will discuss with
Then you'd better
chairman.
have a note like our advertisement for course.
Yes,
You'd better have an additional advertisement saying
yes,
that
yes,
we are having this particular arrangement, which can be
yes,
used as evidence of anybody participating. All the courses will be entitled for course modules, and module will be 5 to 6 or 7 lectures, right?
Okay, sir.
You don't have to come for the whole course, but you can participate in parts. Whatever you are interesting for you can participate and
Yes.
receive a certificate.
Okay, sir.
Okay.
Okay, sir. And also our Vice President, ISL, Engineer Mrs. Kamala Gunawardena has joined. Over to you, madam, for the vote of.
Yeah, Bandhuka, I couldn't hear you properly, but I think I am supposed to do the vote of thanks now. Is it correct?
Correct, madam.
Yes.
Thank you, Bandhuka. I'm happy to deliver this vote of thanks actually at the end of this impressive lecture. And this is the 10th lecture for the session, which is remarkable output from you, Professor.
Yes.
I believe that this is a very effective lecture series together with the interesting and worthy lectures you delivered today and all these 2 years continuously. Thank you very much, Professor, for your intensive and your sharing your knowledge and your sacrifice your recreation time. So thank you so much. Dear participants, I hope you are very much thankful to our esteemed resource person for this enthusiastic presentation, which you could grab much out of his lectures. So as some of your professional development with refreshing the theory and go ahead with the lecture series. So let me thank behalf of you as well, right, to Professor. Also, there's a team behind this screen, and let me thank them as well. First of all, I thank Chairman Civil Engineering Sectional Committee, Engineer Mangal Silva, and Engineer Bandhuka for your efficient coordination and updating each and every lecture in the YouTube and your timely reminders. So those are great, actually. Thank you so much. I extend my sincere thanks to the participants. If you all are not here, this lecture won't be. It should be. Yeah. So because of your attendance, this is very impressive, and thank you so much for your attendance. Though you are grabbing a lot of important things and you are taking home and you are developing your career, but still I thank you so much for attending. Also, I thank the IT team and secretariat and all the support given by the Institution of Engineering Sri Lanka. So thank you everyone, and hope you will have a great day and wish you a good night.
Thank you.
Thank
you very
you.
much, madam. Thank you, sir.